Okay. Yeah. You got the link for the previous week video, right?
Yes, sir.
And also the PDF where I have kept all the derived things that
Yes,
I've.
yes.
Yeah. Okay, then wait for a few minutes to others join, and then we can continue for
Okay, sir.
today's. Okay, then we can start. Right? I think we have waited for 3 or 4 minutes.
Okay, sir.
Start. Okay. So my screen is visible, right? You can see the first page and dates.
Yes, sir.
Okay, that's good. And the pointer also this moving, this pointer.
Yes, sir. It is visible.
Okay. Okay. So good evening, everyone. Today we will discuss about the assignments, and that actually is based on the week 2 lectures, and we will actually revisit some of the concepts, and we'll try to clarify the if you have any doubts about that, and probably we will actually focus on the physical perspective of it, the basic concepts, and try to clear those things. So let's just start. Announcements. This is my website link. You can check me here. This is my website link. And for all the lectures or all the assignments and sessions will be uploaded in this YouTube channel. You can probably now access the first week tutorial sessions, and all the remaining sessions will be uploaded as those things will be done. Okay, so first, so in this week actually, main content of the courses was the Virial equation of state, how the real gas equations deviate from the ideal gas equations, and what are the consequences of that. So, and we will see the problems based on those things. Do check my YouTube channel, and if you consider that it is worth of subscribing, you can subscribe it.
I have subscribed.
Thank you. Okay. So the first question says calculate the volume occupied 2 moles of probably it's not visible here. Okay, yes. Okay, it says that calculate the volume occupied by 2 moles of an ideal gas at 300 Kelvin temperature and 2 atm pressure, where some constant value is given, that this is the universal gas constant R, which value is given in liter atmosphere mole Kelvin unit. So let's just do the thing. Have you tried? Can you do it, or can you give me some hints how you are gonna solve this problem?
I think it will go by the ideal gas equation, since
Okay.
nothing is given. No more information we can retrieve from this particular question. So
Exactly. So as you said correctly, so here since nothing is mentioned, we can start from the ideal gas equations. So what is the ideal gas equations? This is PV is equal to N R T. This is pressure. I'm audible, right?
yes, sir.
Yeah. This is volume. This is the fraction of mole. This is temperature. So what is given here is N is given, which is 2 mole. T is 300 Kelvin. R is given 0.08206 liter atm mole inverse Kelvin inverse. So now if you play with these expressions, then this will be N R T by P. N is 2 mole. This is the fraction of mole. Here is a whole 2 moles are there, and this is P is 2 atm. So this will be absorbed here, and the answer will be, you can do the algebra. I think answer will be something like 24.61 liter. So This is the right answer. Right?
Yes, sir.
Yeah. Okay. So, if you have any questions regarding this, I think it's quite straightforward. It is just extension of the previous class equation of state, or you actually probably know this equation of state from your school days, right? From your school
Yes,
days.
sir.
Yes. Okay. Okay. So then next. Next thing says in virial equation of state, the virial coefficients are function of dash. First option is only temperature. Second option is only temperature and volume. Third option is pressure and volume only. And fourth option is pressure and temperature only. So, any guess? Or
Pressure and volume only.
so you are saying that virial equation of state in the virial coefficients are function of pressure and volume. Why is so?
Because real equation of state we consider only, I mean, it is an extension of the Van der Waals equation of state. So in that state we can see that there is a pressure correction, volume correction. See, in that sense I told that pressure and volume.
Okay, so few things to correct at first. First thing is virial equation of state is it's not extension of thing. It's actually the generic equation of state for a real gas. But Van der Waal actually, Dr. Van der Waal actually gave a model which is used for Van der Waal gasifications. That is that thing. So fundamentally is the in real gas, when we are considering real gas, we will assume few things which were not considered in the case of ideal gas. So that's first thing. And then Van der Waals come up with a great equation of state that actually captures most of the sciences, most of the physics behind all of the gases known that time. And you will be glad to know that he did that work in his PhD thesis. Okay. So that equation of state he actually came up with in his PhD thesis. So let's go to this thing. But your answer is not correct, because when you are saying that you are adding a pressure correction and volume correction, that is included in the equations, right? So when we expand the equations, is there any term in A and B regarding pressure and volume? Is there any, means A or B? Let's say you came up with the knowledge of Van der Waals gas equations. So is where we are considering small a and small b, is there any small a and small b are function of V? To be straightforward about it, A and B, while deriving or while giving giving the concepts, is there any situations where we have written A and B in terms of V, volume V? So if I state it like R, A and B functions of V, or in that case P, were they?
No.
No, that's a good thing too. So here you are right in saying that A is considered for the pressure correction thing and B is considered as volume correction thing. That's right. But when you are talking about this V and this P, these are the pressure and volume of the total system. and these are actually for the molecules. So here let's say this V we will consider as in a jar. If in a jar there is a volume V, we are considering like this, and pressure of the total system is a macroscopic thing, P and V. So actually, to answer these questions, and if you want to dig deep into the concepts, we have to at first address why the real gas equations or the equation of state for a real behavior of gas is needed. So in ideal gas, there are few assumptions, right?
Yes, sir.
Yes. Yeah. What are those assumptions? First, volume of the total system, volume of the system is volume of the container, right?
Yes, sir.
But so here volume of the system means the volume which is accessible to each and every gas molecules. But in real life, if there are finite number of molecules in the system, is it true that those things will be accessible to each and every molecules? Because these molecules have finite volumes, right?
Yes, in that case, we were neglecting the volumes of the
Exactly,
particles.
exactly. So these have some volumes. So from that concept, we will do that volume correction. There is a B which is talking as some kind of, let's say there are two molecules. It cannot penetrate. It cannot penetrate this amount of region. So if it is R, the radius is R, so it cannot access this volume because this has that presence, so it cannot access. So that is one thing. Second assumptions that we tend to forget is in ideal gas there is no interactions between molecules. So that is also not true because sometimes there must be some interactions, and so let's say two molecules are like, if they do not access to whole lot of volumes, they will collide with each other and there will be some attraction repulsions. So because if you say this kind of thing and you try to try to form the potentials, this will be like this. So there will be a certain region which is not accessible. This is 2R, right? And you write the potential, this is not accessible to, this is uh, hard sphere potential kind of thing. This is called hard sphere potential, right? Because this is called hard sphere potential. So whenever you are considering this volume thing, this is always there. Now with, you want to put another kind of thing, probably Lennard-Jones potential, because they can actually interact these gas molecules. So what is the form? Sorry, let me draw it. Sorry, this should not be like this. This should be the Lennard-Jones kind of thing. So there will be a minima, and so after that you can see that this is positive axis says it's repulsion, and this is negative side, this is called attraction. So far, okay, so far whatever we have discussed in that thing, one macroscopic quantity we haven't touched. What is that?
Temperature.
Exactly, temperature. So actually, when we are comparing real gas equations and the ideal gas equations, we haven't talked about temperature, because if you increase the temperature anyway, there will be more kinetic energy, right? There will be more kinetic energy because they will be more disordered, so there will be more collisions. So that's in another point. But when you are comparing this ideal gas and the real gas, we have to talk about at same temperature. Okay, so at same temperature, how those corrections is going to play in this picture. That's why A and B, those correction terms, will be dependent on temperature. Is it clear, the point that I am claiming?
The temperature thing, can you repeat once more?
So far, whatever we have said, we haven't talked about temperature. And this equation of state for real gas and ideal gas should be compared at fixed temperature, because anyway if you talked about two different temperatures, then there will be more disorderedness, because when we are implying you are increasing or decreasing temperature, there will be much more collisions or less collision depending on increasing or decreasing, right? That point is clear.
Yes, sir.
But we want to see how this real gas is going to deviate from ideal gas. So that should be, temperature should be fixed. That's why we're gonna compare those things together. And now at given temperature, how these volume corrections and the interaction correction, which is will be taken into account for the pressure, that gonna change the behavior of the ideal gas from the real gas from ideal gas. So that's why this A and B will be function of temperature only, because all while talking about the equation of state for real gas, we haven't touched temperature. So if we increase temperature or decrease temperature, A and B will be dependent on that. My logics are clear.
Yes, sir. So taking temperature as the reference.
Exactly that point. Because if we I will let's say now I will actually, it will be more clear if we if I say the context of needing an equation of state for real gas. So ideal gas, actually, that is established. Now people, when they are seeing the real gases and their natures, let's say they are measuring the pressure or the certain condition, the volume, there are much deviations from that. So they say this, okay, at first, since we are doing sciences, we will first try to make a model with simpler assumptions and simpler model. But if that model cannot predict all the things, then we will put some other things that will actually correctly predict the nature of the gases or nature of the systems. That's what they did do. So they first thought that there will be no interactions or no things. So there will be the pressure of the total system, volume of the total container. But then there will be they thought that, okay, so these molecules have finite volumes also. So we haven't considered that. So there will be inclusion of the volumes. So we have actually the accessible volume to the molecules, we have overseeded ourselves. We have over calculated the volume of that. That's why they actually, if you say for van der Waals gas, he actually, let's go to the he actually smartly put a V minus NB thing, right? This is volume correction. So the total amount of volume accessible to the molecules will be less. And since the interaction come things, that's why pressure will be also, we have actually taken into account less amount of pressure. So we have to add more amount of that. That's why they added these things. And Professor in his lecture actually explained that thing. So I'm just trying to give you the flavor of the logic. So these things, right? Okay. So this is V minus NB, where the volume correction thing happening, because we have over calculated it, and for pressure we have less calculated, because if there are some interactions, there will be a change of pressure also, and that depends on the repulsive or attractive nature of the potentials. That's why there will be a change of that. So the virial equation of states, the virial coefficients will be function of temperature only, because in this equation of state we are actually comparing the isotherms with ideal gas equations and real the logics are clear.
Yes, sir.
Yeah.
So that potential curve, that Lennard-Jones potential, that one that you drew that above along the positive thing, it shows repulsive interactions, and along the negative part of the curve, it shows attractive interaction. So that one only known as the Lennard-Jones potential curve. I mean, I know that thing, but I do not know the technicalities. I mean, the term.
Okay, so this one or that one.
Left side one.
Okay, hey, this is the schematic of, maybe I have um, I, I drew it pretty badly.
No,
So
no, no, not that. I mean, I did not know that that was only called the Lennard-Jones potential. I did not know the name. I knew the curve, but I did not know the name.
okay. This is called Lennard-Jones potential. Yes. This one. Yeah. Okay. So
Okay.
it actually talks about a very basic concept. So there will be a certain volume exclusion thing, because this volume will not be accessible to other molecules. So there will be repulsion, and then since there will be some thing, some kind of long range. This is called long range attraction potential. This is long range attraction potential. So long range but weak. So actually, if you are, since you have asked it, let's go deeper into that. I should add one page actually. Sorry, blank. Okay, tab. Okay. Okay. So this is actually a culmination of two things. One is sense. Okay. One is this hard.
I've seen this curve in during lattice enthalpy calculations.
Yes. This is, and this is kind of a thing. And if you combine both two, this will be something like this. So something there is, you are something a r to the power 6 minus b r to the power 12, this kind of thing. Actually this will be alpha and beta, and there will be some minima of that and maximum of that. So this kind of thing. Okay. So
Okay.
So
No, in
that's
that
thing.
Bond-Land equation, we had this graph, but I did
Okay.
not know the name that
Okay.
Lennart-Jones.
Yeah. 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 That's true. That's true. It's good. 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 So let's just take 1 or 2 minutes to understand the things and try to see if you have any questions regarding that. Sorry.
So are that hard sphere potential and Lennart-Jones potential are same?
No. No. So in
So what?
hard sphere potential, there is only the volume exclusion thing. They cannot get into the the accessed region which other molecule accessed. But there is no attraction potential. Here is some attraction potential, right? This region there is some attraction potential. If you can see here, this region, there is some kind of attraction thing. Visible my cursory things or not?
No.
Probably
I
no.
mean, the page is visible, but
Okay,
the
okay. So so hard sphere potential, you cannot access this region only. So this is infinite kind of thing. So it goes infinity, but it cannot. There is no kind of a attractive potential. But
attraction. Okay, okay.
here there is some attractive potential. And this is long range. Long range means you know about Coulomb potential, right? This is long range.
Yes, yes.
So let's think about it. Let's give some 1 or 2 minutes to understand that.
So can we say that Lennart-Jones potential is an extension from hard sphere potential, like
Yeah,
that repulsive part is similar to hard sphere potential, and we have added that
yeah,
attractive part as well.
long range attraction. Yes, true, true, true. It's like the basic, basic extension of that was really that it was that, and then you have included something, some kind of potentials, because there are multiple kind of potentials. But when you're trying to model something, when you're trying to get some theory out of it, so you have to first put something, and then on top of that, let's say you are trying to prepare a food, so you will put some thing at first, some basic things, oils and all those stuffs, then some vegetables, and you will start adding some masalas, spices, and after that the cook will be ready. But that thing, when you are trying to model or trying to get a theory out of the experimental thing, then it's quite, step by step you have to put something, because there can be like different kind of potentials also, like complex potentials should be there also. But you will at first try to see what is the main contributions, then try to add the other ingredients of the potentials, and then you will try to get a full picture out of it.
Okay, got it.
Yeah.
Okay, it
Okay.
is all right.
Okay. Okay. Then go to the next problem.
Sorry, your audio is muted.
Okay. Okay. Yeah. Thank you. Thank you. Thank you. Yeah. So, just for like completion, I'm try to rewrite the thing. So here for ideal gas, the equation was PV equal to nRT. Okay. So if you write this like this, P V V prime by RT is 1, right? Where V prime is V by N. So from the previous assignments, I can ask you a quick questions. This V prime, is it extensive or intensive?
Intensive,
Why so?
because it is an ratio of two extensive properties.
Exactly. So if you increase the extent of the system, the volume will also increase, and proportionally number of moles in that also increase. So the
Yes.
molar, this is called molar volume, this thing.
There will be, if there is an increment, the increment will be same for both. Or
Yes.
decrement, the change will be same for both, or it gets cancelled
uh,
out.
Same proportional. Sometimes in some text you can see it like this, or different context, different notations. Okay. So just before coming to this, let's see the problem. The problem says carbon monoxide at low pressures and 273 Kelvin, the compressibility factor Z, which is less than 1, then which of the following statement is correct? Carbon monoxide is less compressible than ideal gas. Carbon monoxide is more compressible than ideal gas. Carbon monoxide is equally compressible as ideal gas. None of the above. What do you think? What should be the thing?
More compressible than ideal gas.
Why is so?
Negative deviation from ideal behavior. So negative deviation means we have to at least compress it to such extent that it becomes an ideal gas, then it will deviate to an positive deviation. It will show a positive deviation. So we had to compress it more so that it reaches at least to an ideal gas, then after that we'll see.
Exactly. So since as Tathagata said, this should be a straightforward thing. This should be this one. This carbon monoxide is more compressible than ideal gas. So, as I've said, so what is Z? Let's say what is Z? Z is actually the equation of state ratio. PV is equal to nRT. This is P V prime by RT. So this is for ideal gas. This is 1, right? Because equation of state in ideal gas says PV is equal to nRT.
In yes.
Exactly. But for real gas, this actually less than 1 and greater than 1. When it is less than 1, means it deviates from the ideal gas negatively, right? If you take 1 minus the smaller number than 1, it will be like minus 1, this
Yes.
will be lesser than that. So here it will be more compressible. This is called also compressibility factor. Less compressible. Z is also called Okay. 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 So, and also Z is also the measure of Z also talks about how real gas deviates from ideal gas. So there can be a good question to ask. So here you can see that is low pressure is mentioned, this low pressure thing. Why so? Why we need low pressure? Why we need low pressure to like the you have probably known this thing, right? When real gas will behave like ideal one. Can you say when it will be? Because I have talked about the assumptions, right? These assumptions. So I can ask a quick question. So seeing these assumptions, when you can say that an ideal gas, a real gas would behave like an ideal one. Just think about it.
At low pressure and high temperature, maybe.
That's the right answer. But can you defend your answer? Like the logic behind this. Let's go to high temperature. Why is so high at high temperature?
Physically, I cannot say. I mean, I don't have a proper thing, but mathematically, I can say that high temperature, the volume correction or pressure correction becomes negligible to their respective pressure and volume thing.
So you are
Physical.
so physical significance. So that's a good thing. So at high temperature, what happens? That they're moving quite fast. Okay, and so if they are moving quite fast, they actually do not reside or did not occupy the specified region of space for a uh, longer time. So they do not occupy the spaces for the longer time. Their time residence at certain places will be less. So it will seem that they are moving throughout whole volume. So there will be the volume thing will be less, right? And also since they are moving so fast, they will collide with each other, and that perfect collisions, and also like the idealistic nature where they're colliding with elastically, that will happen. And why low pressure, that is important, because at low pressure you you are not talking about a great interactions between these two. So the interactions will be less because they are keeping in low pressure. So pressure is not that high. So they are moving throughout the whole volume. Because you are confining it, you are not confining it. It can move throughout the volume
Yes,
freely.
it has no restrictions.
There is no restrictions. So if you apply much more pressure, then they are actually under great stress, because they do not they are actually when they are the force on those particles, the external force on the particles much more. So they are constrained to move in that space. That one thing. And the volume also, since they are moving in a low pressure regime, they can access that. In those perspective, you can say that it can behave like a ideal gas, right?
Yes, sir.
Yeah, let me go to this thing. So let's go to the next problem. Which of the following statement or statements are true about Boyle's temperature? First option, at Boyle's temperature, the second virial coefficient is 0. Second option, at Boyle's temperature, the compressibility factor Z it is approximately equal to 1 for a range of pressures. Option 3, the Boyle's temperature of a van der Waals gas is given by the formula Tb is equal to A by B R. And option 4 is all of the above. What will be your guess, Tathagata?
All of the above.
All of the above. Okay, I think you know that. Let's do it. Let's do it together, and you can help me whenever I can ask you any questions. Okay, so let's just start from this thing. Okay, so what is the okay, where is should be, yeah. So this is the equation of state for van der Waals gas. Okay, we will actually do it in molar volume thing, that will be easier, or like there will be much less expressions to handle. By V prime, this V prime is molar volume, so V minus this will be R and T. Let's just divide the whole equations by this term. So what that will give is, will give P plus so you can actually follow the steps, and that will be easier when you are calculate for your exams or something like that, because you know, let's follow the steps accordingly, right? Just divide by whole thing.
Yes.
Yes, so this will be P by RT P prime minus P minus A by V square. Let's divide the whole thing with RT. What that will give is P by RT 1 minus V prime minus P minus A V prime square RT. Let's multiply V prime to both sides. So this will be P V prime by RT 1 minus B by V prime minus A by V prime RT. So this can be
Yes, written as Z.
no, this can be expressed via this can be expanded into binomial form.
Yes, yes. 1
So
plus 6 plus x square.
so this is RT. So this is nothing but 1 minus x to the power minus 1. So this will be 1 plus B by V prime plus B by V prime whole square and dot 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 this expression. So A by RT into 1 by V prime. We will actually rearrange these things according to the power of this thing. So if you consider these two things, this will be minus, right? This will be minus. So from these two things, you can write. Let's go to the another page. Actually, that will be a good thing. Let's add one page. Okay. Okay. So what we have got is P P P prime by RT is equal to 1 plus B by B prime, so 1 by B prime common. This will be B minus A by RT by B square B prime square, a higher order term. Now, the question was, at Boyle's temperature, the second virial coefficient is 0. Now, this is actually quite straightforward. Let's first understand what is Boyle's temperature. What is Boyle's temperature? Do you know?
Physically, I don't know. I mean, physical significance.
I will come to that. Let's just get from the mathematical point of view.
The temperature at which the second virial coefficient is 0 is Boyle's temperature.
Yeah. So that's the quite definition, right?
Yes.
Definition is Boyle's temperature second virial coefficient is 0. So okay, for the completion I should tell this. So this whole thing is called second virial coefficient. It is written as B of function of t. This is called third. This is called C t, and so on and so forth. Now it is clear, right, Tosagato, how this temperature dependence is coming?
Yes, sir. From the second question.
Yes. So all these virial coefficients are temperature independent, temperature dependent, because there should be some B and these things. These are depending on this. So second virial coefficient is 0. That is called Boyle's temperature. So first option is correct. Okay. Now this says at Boyle's temperature the compressibility factor Z is approximately equal to 1 for a range of pressures. Why is so? This is because for this, since pressure is related to volume, and you can see the leading order contribution will come from only these, and higher order these things will be very less affected to this thing. But if this coefficient is 0 for this expression, we can get 0 from this, and there will remain only 1, and other contribution are very negligible, right? Because
Yes, sir.
this
Because
one,
P becomes very large and
yes,
the square terms are also larger as it is in the denominator part, so it becomes negligible.
yeah, so this will be this time, so on and so forth. So that's why we can say that it will actually it will behave like an ideal gas if Bt is 0. Now, so far we haven't talked about what is Boyle temperature, the expression. So since Bt is 0 at Boyle temperature, then this expression B minus AR Tb, which is Boyle temperature, I have expressed in this way, will be 0. Then from here, A by R Tv should be B, and we can see Tb will be A by Br.
Third option is also correct. So
Also correct, exactly. So from these two things, we can say that this also correct, this also correct, this also correct. That's the thing. So main thing will be all of the above. This will be right option. Now, what does this expression that second virial coefficient equal to 0 mean? What will be an educated guess? Because I'm trying to engage you guys, because that's when your perception about these things will grow. Because you will give a right or wrong answers, and I will ask the logic behind it, and I will correct you guys. Then those things will be actually engraved in you for a longer time. So that's why I'm asking, what will be your ideal guess? What does happen in ideal guess? There will be no interactions. I'm giving you one clue. There will be no interactions in ideal guess. So if this B term, this BT, second virial coefficient, is 0, what should happen? Think about it. I will give you 1 or 2 minutes. Think about it.
One thing that I can recall from the lectures of Arnab Mukherjee sir is that he told one thing that in the PT can only be 0 when the attractive interaction and repulsive interactions becomes equal.
Yeah, you're right. You're right. Yes,
So
absolutely right. That is the thing. Because let me actually let so can I dig deeper into those things? Like I'm
sure,
going to give, yeah, I'm going to give one more perspective. You know, these terms, these BT, CT, and all those terms, they actually talk about a good thing. What does it think? Let's say this is a small molecule. This BT talks about the pair interactions. Means in a volume V, BT talks. BT says interactions between pairs of molecules. Because if there are n molecules, how many pairs will be there?
n by 2.
No, there will
Sorry,
be
2
n.
n 2 n 2 n 2.
No. There will be NC2. The combinations you have to take. N into n minus 1 by 2.
I'm quite
Because
bad at permutation.
no. Let's nobody is bad. You have to just, because the teachers is bad. Let's say there are 3 things. Okay, 1, 2, 3. Okay, let's count how many pairs it can. One pair will be this one pair will be this one pair will be this one. So how many pair is 3? What is the formula? NC2. Let's check if the formula is right. So this is 3C2, means 3 factorial by 2 factorial by 1 factorial would be 3. Let's talk about 4, because this is trivial 3, but when we talk about 4, this will be a quite interesting thing. How many? This, 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 this. Is it completed? No. There will be this.
Yes, diagonal things also, yes.
So 6. What is this formula? 4c2. This is 4 factorial by 2 factorial by 2 factorial. This is 4 into 3 by 2, 6. So if there are n molecules, there will be nc2 number of pairs. Let's come into, it's clear right now?
Yes, yes, now it is clear.
Yeah. So in that same extension, if there are n number of molecules and you want to count how many triads are there, triads means we cannot call it pair. Then there will be a system of 3 molecules. We are counting the system of 3 molecules. What will be that?
Yes, yes,
nc3.
triads.
That will be nc3, right?
Yes, yes, because
That will be
once in that periodic table thing, we had read one thing, Dobernier's triad.
so this will be a nc3. For if you want to see interaction between 4 molecules, this will be nc4, like this one. So bt actually talks about how those pairs are going to be interacted, or how those pairs talk to each other. Talk to each other means they are interacting with each other. So bt actually talks about the pair potential. So when bt is 0, we can say that the attractions between those molecules and the repulsions due to the volume exclusions will be equal. Okay, we are actually in that, we can say that only when we are saying that this higher term is negligible, because this also contribute to the fact, but this will contribute to very minimum, bare minimum. That's why we can say that bt when is 0, there the interactions for so this thing, this one, this is actually the repulsion term, because this is, you cannot get into this amount of volume, because this volume is for the volume exclusion volume exclusion means there are a molecule which has a finite volume. So this term comes from the repulsion, and this comes from the interaction. This is called attraction. So these two, when these are equal, you can say that this bt is equal to 0. Okay.
Yes, sir.
So let's say jth term. So then you can extend the idea and say the jth term or jth coefficient, the jth virial coefficient talks about the interaction between the system of j molecules in volume V. System of j molecules means here that I do not know the exact term. Here the pair, triad, and this kind of thing. You can say like in terms of j molecules in a volume V, means there are j molecules, and what will be the interaction between that system only. There are n molecules, but among the n molecules, if you choose j molecules, how the interaction pattern or interaction picture is for those j molecules. So
Okay,
then
like in this case, we are taking only two molecules. In that case, we are taking J molecules.
j molecule. So there will be a combination of NCJ. So there will be this number of
Yes.
j molecule system. Okay. So
Okay, sir.
jth term will be that. So I have actually given lot of things. Let's just take 2 or 3 minutes to understand. I will keep it the slide here, or if you say that I have to shift the slide into the previous one, I can do that also. So let's just keep it here, and if you have any question or clarification regarding this, we can address it. Let's take 2 or 3 minutes.
It's all right, sir.
Okay. 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 One thing, so if we actually from strict perspective we want to say when this virial equation of state will actually will actually fall into ideal gas equation of state, then all the coefficients needs to be 0. But here we are saying, let's say, is it feasible that all the things will be occurring into 0, because this is a rare occurrence. But
Yes, that's why
so
ideal gas is not practically possible.
yeah, practically possible. So we have to take into account like what are the most significant term in that, that is bt. This is second virial coefficient. This is the actually this is from where the most contributions comes. That's why we have to make 0, and we can safely say that this is okay. Okay, sometimes in the research fraternity, when you want to find, you want to probe more into that. Probing more means you want to find a rare event, you want to find a small fluctuations, then you have to take care of that. But when you are talking about the total system or the macroscopic thing, and also like you are taking the leading order term, then you can safely say when bt equal to 0, the second virial coefficient is 0, the virial equation of state will actually will become the ideal gas equations. Okay. So
Okay,
there are
sir.
some few assumptions, because we scientists actually take some liberty, uh, and we'll assume some things, because let's say like these assumptions, it is very quite important. Let's say you are this is quite good thing. I want to give some insight so that you can understand this quite better. Let's say you want a tea without sugar, and some amount of that, not a whole 100 ml or something amount of tea, you want to some amount of that, and you put one sugar cube there. The effect of that sugar cube will be important compared to when we are putting that sugar cube in a 1 liter of sugar free tea. That importance will be less, right? When we are
Exactly, because the volume matters.
volume matters, because the importance of because the contribution, the ratios of that will be less. Let's understand in another way. You are eating a sweet, let's say rasgulla, and then you are eating one small tiny sugar cube. That sugar cube doesn't have any meaning in when you are taking the leading order term, right?
Because Rasgulla is more sweet
It's more sweet.
than
Okay,
upper. Yes.
exactly. That's the thing. That's the thing. So you have to sometimes you have to think about that. And now let's say, and now you can ask me, so when it will be important? It will be important when you are talking about some preparing a solid. That will never be important. But if you say what kind of like you want to probe, let's say sugar in that sweet is different. Let's say hypothetically, I'm not talking about chemistry, the sugar in that sweet is different and the sugar cube we are putting is different, and you want to probe what type of sugar is there. So then you are, when you want to probe for the sugar cube, the sugar type of the sugar cube, then you have to talk about the other terms, right?
Exactly.
Exactly. So what we want to study is more important. When you are talking about thermodynamics, we are talking about the macroscopic approaches.
System is important.
Exactly. System is important. Okay. Okay. So here is a question. So, question is, the van der Waals equation for NH3 at very high pressure reduces to PV prime RT minus PV, PV prime RT minus A by V, PV prime RT plus A by V square, PV prime RT plus PV. What is your answer, or you want to do it? Because I have given you.
Yes, from the lecture series, I can say that at very high pressure, A term becomes negligible.
Hmm. Okay.
So B terms even, so P V minus B is equal to RT. So if you rearrange this, I think
Hmm.
that will be last one. PV prime is equal to RT plus P. Yes, last one.
Okay. So just take 2 or 3 minutes to, like, if you can derive it. If you have pen and paper, you can derive it, right?
Yes, yes.
Like take 2 or 3 minutes. Okay.
Okay.
Yeah.
Okay, sir.
Okay. Yeah. What is your answer?
So you are not audible. Your audio
Yeah.
is
What is your answer?
last one only. PV
Yeah.
bar equal to
Yeah.
RT plus.
It's quite simple, right?
Yes, yes. Pressure
Yes.
correction
Yeah.
becomes
Yeah.
negligible because high
Exactly.
pressure we are
Yeah.
mentioning.
Exactly. So so our This van der Waals equations is P plus, let's A by B prime square and P minus B RT. Now, when P pressure is high, then we can say this P plus A by B prime square is nearly, this is P. So what that would be, P B minus B R T. That becomes PV prime is equal to RT plus P. Oh, this will be option 4. Okay, so that's it. Okay, so let's go to the next problem. Is it clear, the problem? I think you have done it.
Yes, sir, it is clear.
So this problem says calculate the pressure exerted by 2 moles of carbon dioxide gas in 1, this is called decimeter cube, that is actually 1 liter, 1
Yes.
decimeter cube vessel at 323 Kelvin using the van der Waals equation of state. The van der Waals constants for carbon dioxide A and B and C, this is R, and what will be the pressure? Can you do this quick? Then we can check
Yes,
the
just putting
answers.
the formula. Okay. Putting the things into the formula.
Yeah, yeah.
Last one, 43.59 again.
Okay, let's check with me.
That again you are
Okay,
not.
okay, let's check with me. Yeah, 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 yeah. Thank you for reminding me once again. Okay, so again, these equations, you want to know the pressure. This P plus what are given, n square A B square B minus NB equal to nRT. That makes, so let's first calculate V prime, then that will be easy. V prime is V by N. N is, V is 1 liter, right? 1 decimeter cube.
Yes, yes.
1 by 2, this is 0.5. And since we have written it another way, sorry, P then will be RT by V prime minus B minus A by B prime square. So R is given 0.08206, T 323, B prime is 0.5 minus B is 0.0427 minus A by 3.3.59 divided by 0.5 square. Let's check it with my calculator. Yes, so it is coming last option 43.59. Yes, this is the right answer. For the completion, I should write the exact result. For me, it's coming 43.587. Okay.
Yes, sir.
Yeah. Okay. Same again. This let's read it out. At extremely high temperature, the van der Waals equation of state reduces to PV prime RT minus PV, PV prime PV equal to R, PV prime equal to RT, PV prime RT minus A by V square, PV equal prime RT plus A by A V prime square. So, what should be your guess? What should be your guess?
It becomes an ideal gas.
Exactly. So that should be PV prime is equal to RT, right?
Yes, sir. Option B.
So here at high temperature, so at high okay. Okay, let's go to the 8th problem, which says calculate the change in internal energy of an ideal gas which undergoes expansion against a constant external pressure of 1 atm. Its volume increases 10 dime cube to 30 dime cube. This is liter, let's say, decimeter cube. While undergoing expansion, the gas also absorbs 1030 joule heat from surroundings. So we have to calculate the internal energy. So what do you think? What should be that thing?
Sir, your voice is mismatched.
Is it audible?
Audio.
Right now it's audible.
It is audible, but the video comes a bit later.
Okay, some lag, I think probably that's why. Right now? Now?
Check once.
Huh? Yeah. I didn't hear you last time. Hello?
Hello.
Hello? Probably the internet, I think internet is sometimes it's fluctuating. That's why. Okay. Yeah, probably for internet correction. Now I am audible.
Yes, sir, you're audible. I just And rejoined again.
Yeah, that's good, that's good, that's always great to rejoin. Okay, so so what would be, like, we have to let's just address the problem. So what do you think, what is this problem actually wanted to know from you?
Change in internal energy means
Let's
du
say any
or
law
del.
associated, any law associated
First law,
with it.
first law, first law of
Yes,
thermodynamics.
yes, true. And then so from first law of thermodynamics we wanted to, we can get all those things, right? So just
Yes.
go though. So what does first law says? So actually this is from first law of thermodynamics. So a quick question. So first law of thermodynamics talks about a good, secret principle of physics or chemistry or any science. What is that?
Law of conservation of energy.
Exactly, law of conservation of energy. And what that law says, just state it for once.
That conservation law.
Yeah.
That energy can neither be created nor be destroyed, and it can
No,
only be transferred
not
from.
like in the mathematical form.
Oh, so
D,
mathematical. I
dw,
mean, in first law. Acha, dw plus dq is equal to u.
dw plus dq is equal to
Is equal to u. I thought
p.
that you were asking about the conservation law.
Okay. Now I want to ask you two questions. So these are, is this perfect differentiable or this,
No, no, there will be a dash
there's this one,
path function.
this will path functions. So one thing is been given, which is dq, right?
Yes,
D,
dq is
dq is given
yes, yes, dq is
1013 g. We want to calculate dw. External pressure is given, so this
change in
is,
volume is also given.
change in value is also given. So just let's just, what will be the function? This will be minus p
pdv,
external
dv,
pdb,
yes,
pdb. So this will be final volume,
v2 minus
initial
p.
volume. So this will be p external, which is 1 atm times 20. Let's, this will be 20 dgm cube. So this will be minus 20 into 101.3 joule, or we can write as 2 into 113 joule. So now you can see, right, this change in internal energy will be minus 2 plus 1013 joule, that will be minus 1013 joule. So this will be this one. Now can you physically say why it is happening? It's absorbed some heat, but the internal energy decreases. Why is so?
Because it does some negative work. I mean, the system does some work. So the internal energy, the content.
So it expands. So when it is
Yes, yes,
expanding, so it is, systems is doing some work.
yes,
So as a result of that, it loses its internal energy, because that
yes,
internal energy actually converts to work done by the system. We
yes, yes.
physically want to think. Yeah,
Summation value decreases.
true. That's the thing. So option B is correct. Okay, let's go to the another problem. Okay, so the problem says a gas obeys the equation P times V molar volume minus B, V bar by minus B equal to RT. What will be the expression for reversible isothermal work for this gas? So you know the reversible isothermal gas for a,
Yes, yes.
what
Ideal
is that?
gas.
What is that?
Minus RTLN V by VA final by V initial or V2 by V. Same here,
Okay.
the B terms comes and V final minus B and V initial.
Okay, then what will be the option for you?
A. Option A.
Option A.
Option,
Okay.
option A. Yes, yes. Option A contains two ln. There should be one ln.
There will be 2 ln. Why?
No, there is two.
Okay, that is actually just
अच्छा
ignore
अच्छा
it.
मिस्टेक ओ अच्छा
This.
अच्छा अच्छा ठीक है ओके
Okay. So let's just this thing. At first, we have to understand what is isotherm called. So this is at constant T. So isotherm means constant temperature. So isobar, this has got some processes. Okay, isobar is constant P. One process is called isochoric process. What is that? Do you know that?
कांस्टेंट वॉल्यूम प्रोसेस
Volume process. Okay, and there is also
एडियाबेटिक प्रोसेस
adiabatic. What is that?
कांस्टेंट हीट और नो हीट चेंज और
dq
yes
is 0.
zero
So these are the processes, fundamental processes. Let's say we know what will be the dw. Sorry. dw is minus pdv. We want to know the w, total w. So this is will be whole for, this will be initial and final. This is pdv, so pdv. So minus vi, va. P will be rt minus v prime minus b dv. We can write it as vi minus va rt v minus b. So we can write this thing, right? This in this way,
yes
because
yes
this
b
is
minus
constant.
b yes
So this will give you, this is dx by x, this is log x, so minus rt log, sorry, minus rt ln. This will be, first thing is vf minus p vi minus p. So this will be the first option. This, okay, quite easy. Okay, let's go to the last problem of this set, which is calculate the work done in reversible. So what is this one process is reversible? Reversible, isothermal, compression. So three things. One is reversible, one is isothermal, means constant temperature. One is compression. Compression means volume is decreasing. 5
yes
moles of ideal gas at 300 Kelvin from volume 20 decimeter cube to 10 decimeter cube. Can you quickly do this?
okay
Yeah.
third option, 8.643 kilojoule.
Okay, okay, okay. Let's check with me. Okay, so this option says the mole is 5, temperature 3, and 22 10. 300. Okay, let's just quickly write it. N is 5, T is 300, K, and V 20 10 T. So work done. Then at first we need to know that so isothermal, that's one thing, and also reversible.
The same formula will be applicable, just the sign will be changed because here V2 is less than V1.
Exactly. So then this will be RT, means nRT ln of VF by VI with minus sign. Then if you talk about same thing, that will be also like this thing, minus RT ln of VF by VI, right? So what is that? RT ln VF bar is 10 by 2 and VI bar is 20 by 2. Ultimately, this will be RT ln of 0.5, right? Because this will be 10 and this will be 20, and if you take this 0.5, so this will be minus RT ln of 0.5. So you have taken the R value from the previous thing, 0.0826. Okay. Oh, sorry.
Yes, that's why my answer came a little bit different, like 8.5 something. So I thought it is the nearest. So I thought
So you took R value is something like 0.
I
How
took
much?
0.08 to 1, 6
Okay,
nearest
okay,
to
okay,
convert
okay,
it.
okay. So this is 0. Sorry, there is a minus. Sorry. The 6.93 answer times 300. Yeah. So if you take that, then it would be probably, I'm goofing at somewhere, ln of 0.5. This will be minus of that, and 48 answer times 0.08206 and 300. Anyway, the
So
formula
you
is right.
forgot the mole, I think. Oh, you just put it. Yes, you forgot the mole, I think.
Mole, I think that will be n somewhere else.
Yes.
This
No,
will be
A minus inert T LNV, fine.
LNV, and this will be this one, like this.
I
And
at first I thought that you put,
no,
I
no,
mean you took that N in that molar volume thing
no,
and
no,
you
no.
took.
This formula is right. This bar will not be there. So this will be around
Yes,
2,
yes.
and if you took that, this will be around this. Okay, so you can do the algebra, but the
Yes,
basic.
yes. Calculation we can.
Okay, so that's thing. Now we will see some few further problems. Probably these are on the extra assignment thing. Let's take those things. Okay, so it says 100 liter of an ideal gas is allowed to expand isothermally against a constant pressure of 1 atm until its volume becomes doubled. The work done is given by. So these are the same thing. So
Yes, same formula based
same
questions.
formula. One thing is it cannot be written as constant pressure because it is this isothermal means temperature is fixed, T is fixed. So constant pressure is not possible, right?
Yeah, exactly. So the term is not well defined.
Well defined. So this is a problem is wrong. But if it is, so you can do one thing. I'm not going into the algebra. So if it is T is fixed, T is fixed. In that case, the formula will be minus nRT ln V final V initial. When P is fixed, an isobaric process, this will be minus P external P minus Pi. That's all. Okay.
Okay,
So
sir.
you can do the calculations accordingly.
Yes, I would say.
Okay. So the next problem. Next problem is in a cyclic process, which of the following is true? Work done is zero. Work done by the system is equal to the quantity of heat given to the system. Work done doesn't depend on the quantity of heat given to the system. The internal energy of the system increases. What do you think? What do you think? Hello?
I think work done cyclic process, so the work done should not depend on. Let me think once. 1 minute.
Let's,
Can you please?
yeah. I can draw the picture in the meanwhile.
I think it should be B.
So work done by the system is equal to the quantity of heat given to the system.
Yes.
Okay. Let's inquire. Okay. So in cyclic process, work done is not zero because it you are doing some because it is path function. Okay, it depends on the path you move. So it's not zero. So work done is not 0. That's one thing. So this is wrong. Let's work done by the system is equal to the quantity of heat given to the system. That can happen because dW plus dQ equal to du. Since internal energy depends on the state of the system,
So it becomes 0.
so this is 0. So this is actually equal to that. Means the amount will be same, the minus sign will
Yeah.
be different.
Yes.
So this one option does not depend on the quantity of it. This is wrong. And internal energy system increases. This is wrong. So this option is right. So you are
Yes, I
absolutely
agree with
correct.
the same logic.
Yeah, that's good. Okay, so let's go into the last three smaller problems. That says internal energy of liquid is less than that of a gas at the same temperature. So let's just think from the physical perspective. When you are taking ice and try to convert it into water, you actually give some heat, and that ice melts and water becomes. And then you want to steam out of that. You put further heat to convert it in vapor. So from that perspective, internal energy of liquid is less than that of a gas at the same temperature. What your point? Is it true or not true?
So you are telling that let's take the liquid to be water.
Yeah, or any kind of thing, because
Okay, same
in
thing, same phenomena for
in
everything.
liquid there will be bonds, right? There's some kind of structure will be there.
Yes, intermolecular attraction should be more.
More. And gas, there are free gases, there will be no that such kind of strong interactions. So internal energy of liquid is less, obviously, than gas, right? Because when there is bond,
Kinetic
it
energy
uh, when there is bond,
factor
it
comes into
actually
play.
uh,
Restricts the motion.
most motions, and also it actually relinquishes some energy and makes the bond, right? It actually, when you are trying to do something and you want to the latent heat concept, it goes to ice, but it actually
Temperature
something,
remains constant.
some amount of heat actually it rejects, or it emits. So this is be true, right? Energy of liquid is less than of the gas. Okay. Internal energy of perfect monoatomic gas at 300 Kelvin is only kinetic energy. What your point of view? Hello.
Monoatomic gas means it only has
Only the
translation on
gas.
degree.
Yeah. Yeah. Yeah.
So it is true.
It is true. Yes, it is true. It is true. It's quite pedantic. It's true. Last question
It is
is
false because it is not monoatomic.
the internal energy of water at 300 Kelvin has only kinetic energy. Or not only monoatomic, there is also like the bond energy and all those stuff.
Yes, yes.
It's a structure and all those stuff. So there will be this thing.
Because in at theoretical Kelvin it exists in liquid form.
Yeah, yeah, sure, sure. That's the thing. Okay, so this will be also. This is also like internal energy of care has on. What was the option? Because I cannot see it. Has only kinetic energy. False. This is false. So this is false. And just for completion, I will need water as bonds. It has H bonds, right? Hydrogen bond also.
Exactly.
Has energy, vibrational, all those stuff, etc. So the statement is false. Yeah. Okay. So thank you. So far,
Thank you, sir.
this is the thing. Okay, just wait for a few minutes. Okay, so this is the end, and you will get the videos from the YouTube channel. Okay.